All right, how's it going out there, folks? We've been jumping into the seasons, as you know. You guys went to science court not long ago, right, to figure out why we have seasonal changes, and hopefully you recall that's from the tilt of the Earth, right? Not from the changing distance to the sun, but from the tilt of the Earth on its axis. Uh, we're going to look a little more into seasonal changes today. It's one of my favorite pictures as well here. Take a look at that tree there, right? The same tree the photographer took a picture of at 4 different times of the year and then juxtaposed it on one image. You got to love that. Really cool. All right. Here's your classic Earth and space diagram going through the seasons. Notice the counterclockwise orbit when viewed from the North Pole perspective. All right. We're going to start out with a kind of a funny little street style interview at a Harvard graduation where the reporter goes around asking the graduates what they think the cause of the seasons is. Everybody gets caught off guard with questions, obviously, but some of their responses I think you'll find funny. Check it out. Sorry about that delay.
Causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get further away from the sun.
These graduates, like many of us, think...
No, they were not right. Right, it's all about tilt, folks. All about tilt. So read this little blurb here. That tilt of 23.5 degrees, of course, is the cause of the seasons. But you got to combine it with two other things. So there's the tilt of the Earth's axis as it revolves around the sun, but then its ability, of course, to keep that tilt. And that's a new term we'll introduce to you here called parallelism. So read this blurb here. Hit pause. All right, so why do we have the season? You can see the tilt here, and it keeps its tilt all the way around, that 23.5 degree tilt. They call that parallelism. But the tilt, of course, is the major cause of the season. If there were no tilt, there'd be no seasonal change, right? Every place on Earth would have the season that it's currently in. So the equator would always be summer-like. Elmont would always be spring or fall-like. Okay? The poles would be cold, and you wouldn't get that change. All right? Second, of course, it's got to revolve around the sun. If it was just tilted in space, then only one hemisphere would get the direct, and the other would always get the indirect. Okay? Not to mention the sun's gravity, of course, would pull it in and destroy us if we weren't revolving around, but we'll save that for astronomy. And there's that new one for you, parallelism. The idea that the Earth keeps its tilt throughout the year. Now, I'm sure you've all played with a top, right? When you spin a top, it starts to wobble. Well, Earth is like a top. It does wobble, but it's a very slow wobble. It takes 22,000 years for the Earth to wobble one time around. Of course, that means in the next 11,000 years, these seasons would be reversed. But in human time scale, obviously nobody's living that long. So we just say that the Earth keeps its tilt. But yes, it does wobble. It just takes a really long time to do it. Okay? Anyway, so the ability for it to relatively keep that tilt, we call that parallelism. Okay? Read that blurb real quick. How does the tilt affect the Earth there? As your sun rays coming in, and you can see the northern hemisphere getting direct rays and the southern getting indirect rays, and the thickness of those lines is, telling of that. Now, this is when the Earth's on the other side of the sun. It doesn't just switch like that. It revolved around, right? This is 180 days later, and now you can see the southern hemisphere getting the direct rays of the sun, whereas the northern, not so much. Okay? Because the Earth is tilted, the North and South Pole receive different amounts of sunlight, and of course, there'll be opposite seasons, right? The tilt determines what season you're in. Okay. What would happen to the seasons if we were tilted more, right? What if we had a 33.5 degree tilt? Well, what do you think would happen? Would it be the same? Different? What do you think? Well, it turns out the more extreme your tilt is, the more extreme the seasons are going to be. So let's say we do go to a 33.5. Well, that means our winters are going to get a heck of a lot colder now because in the winter we're tilted more away from the sun. But in the summer, we're going to get even hotter because now we're tilted more towards the sun, right? It would be more extreme seasons. And of course, the opposite would happen if there were no tilt, right? If there were no tilt, no seasonal change. If there were less tilt, well, then it would be more moderate seasons, right? Your winters wouldn't be as cold, your summers wouldn't be as hot. Okay? Okay. And there it is. You'd have more extreme seasons, colder winters, warmer summers. The latitude of the tropics, right? It would no longer be in between 23.5 degrees north and south. It would extend to 33.5 degrees north and south in this scenario. Because the tropics are the areas of the Earth that receive direct sunlight at some point throughout the year. Okay? What would happen if there were no tilt at all? Well, what did we just say? You got it. There would be no seasonal change. Okay? All right. The direct ray of the sun would always hit at the equator. They would always be in summer. Elmont would always be in a spring-fall scenario. And you wouldn't have to change your wardrobe seasonally. All right. Does distance affect the seasons? Well, there is a change of distance, right? The Earth's orbit is not a perfect circle. It's elliptical. Again, we'll talk about orbits and shape of orbits and astronomy that we're getting into. And yes, there is a difference here, right? 147 million kilometers versus 152 million. But that slight difference, right, relative to the whole distance, that slight distance doesn't really make that much of a difference, right? The light is still traveling in space at the speed of light, still makes it to Earth in about 6.5 minutes, still hits the surface, absorbs the same way. That little difference in distance doesn't really change much. They give them some nice words, right? When you're further away, A for away, they call that aphelion. And when you're closest, they call it perihelion. The sun will look bigger, right? Because you're closer at perihelion and a little smaller at aphelion because you're further away. But temperature-wise, it really doesn't change much. Down here, you see a really cool shadow effect. Obviously, the sun must be on the lit side, and the shadow is the dark night side. They ask you to draw that a lot, right? Where would the shadow be relative to the sun? Well, always opposite of the sun is nighttime. Okay? And there it is. Distance does not affect the seasons. We are closest to the sun during wintertime, actually, right? So, really, there's no difference at all. All right. So, you guys got to fill in this chart. And then there's some summary questions after that. It's going to ask you to shade in the dark areas. Remember, that's always opposite the sun. Make sure you label your latitudes. It's going to ask you for hours of daylight. How many hours of daylight are these places getting at this season? My advice would be to start at either summer or winter, right, and work your way around. Take note of the tilt of the Earth's axis, right? That stays the same, right? It's the same tilt as it goes around the sun, so it's just relative different. Okay? So polish that up and your summary questions, and we'll go through it in the meet. See you there.